All right, so our first lesson on similarity and similarity proofs had to do with angle-angle similarity, and that you could prove two triangles similar if you could find two angles within each that were congruent. Today we're going to talk about SSS and SAS similarity, which brings to the idea that if you can figure out things about sides, you can also state that triangles are similar. But before we get to that, we're going to do one type of transformation, well, technically three transformations on this coordinate grid, is just a kind of review. So I'd like you to quick pause the video, do this opening exercise, and then come back to the video and you can check your answers. All right, what you should have seen happen is you take DRG and then you apply this composition. And when you do this composition, you have to remember that a composition with those O's means you go right to left. So first, we start with this rotation of 90 degrees. And if you have a rotation of 90 degrees, it takes the point XY, reverses the coordinates, and negates the first one, so it becomes negative YX. So DRG, which starts off with these coordinates, becomes that. Then the next thing we're going to do is this reflection across x equals negative 1. X equals negative 1 is this line right here that I'm highlighting yellow. So what you can do is plot the points right here, D prime, R prime, G prime, and then look at the picture and flip them over that vertical line, which will get you these next coordinates. And then, last but not least, we have a dilation of O negative 2. Dilating really just means you multiply your coordinates by negative 2, which gives you this final set of points. If you are struggling with those, you need to come in for help. This probably should have taken you somewhere between, I don't know, 5 and 8 minutes to do, hopefully less than 8 minutes. If you are unsure of your coordinate transformations, make sure you come in for help. All right, now the next question was, is this a similarity transformation? And yes it is. To answer this question, yes, it's a similarity transformation because it includes a dilation. All right, so getting back to that idea of similarity, yesterday we said AA defines something as being similar. Angle makes two things similar. So what else we can say now is instead of only using angles, we can use sides as well. So if two sides of one triangle are proportional to two sides of another triangle, and if the included angles of those triangles are congruent, then the two triangles are similar. And this is called SAS similarity. So what does that look like? SAS similarity. Well, this is what it looks like. I have these two triangles. I don't know all the angles. I know one of the angles, and I know the surrounding side. So I have two sides in the included angle. Now, if I want to show that that theorem up above holds, I need to show that these pairs of sides are proportional. So option 1 for showing proportionality would be to say that my first two sides are 3 and 2.5, and my next pair of sides are 6 and 5. 3 over 2.5, 6 over 5. If I put 3 over 2.5 into the calculator and math fract it, I get 6/5. 6/5 obviously equals 6/5, so the sides are proportional. And 70 equals 70, so the included angles are congruent. So, by SAS similarity, triangle XYZ is similar to triangle ABC. Now there's two, well, more than two, but two major ways to set up your proportions. One way to set up proportion is basically within triangle fractions. Two sides from the same triangle go on one fraction. Another way to do those proportions, and the way that I usually lean toward, is this option where you say, all right, I'm going to take the smaller side of the first triangle and compare it to the smaller side of the next triangle, and then see if that's the other side's the same thing. So 2.5 to 5 is a half, 3 to 6 is a half. Yes, these are proportional. So my point in showing you this is basically the idea that these proportions can be set up in a bunch of different ways. You're looking to see, though, if the two fractions are equal. Alrighty then. So, on example 2, use the figure below to answer the following questions. Name and state all the triangles you see in the figure. Draw and label each triangle separately. I'm just going to do this quick. So, what are my triangles? There's 2 of them. There's triangle ABC, and there's triangle A, B prime, C prime. In other words, this top guy right here versus the whole thing. Fine. Are the corresponding sides of these 2 triangles proportional? Show the work that leads to your answer. So, corresponding sides. I'm going to say, well, the top triangle has a left side of 4. The whole triangle has a left side of 4 plus 9, which is 13. The top triangle has a right side of 3. The right side of the big triangle is 9.75. I want to know if those things are equal. So 4/13 can't be reduced anymore, but 3 over 9.75 math fract is 4/13. So I have 4/13 equals 4/13. And these 2 triangles share angle A, right? So the sides are proportional. Are the included angles equal? Yep, they are, because angle A is congruent to itself. And why would that be? Oh yeah, because of the reflexive property. Duh. And then are the 2 triangles similar? Yes, they are, because I have 2 pairs of proportional sides and 1 pair of included angles that are congruent. So they are similar, and the first triangle is ABC, and the big triangle is A, B prime, C prime. All right, determine whether 2 similar triangles exist in figure 2. I want you to set this one up on your own. So I'm going to actually stay silent for a second. So I'm going to count to 10 in my head. I want you to try to set up a proportion on your own. Ready, set, go. Okay, I counted to 10, but I did it kind of fast. So, on this one, I want to compare sides here. So I'm going to take 2, which is the smaller side of the top triangle, and then I'm going to compare it with the smaller side of the big triangle, which is 9, and then 3, which is the bigger side of the top triangle, and the bigger side of the whole triangle is 13. Is 2 9ths equal to 3/13? No, no, it is not. So the sides aren't proportional. Therefore, the triangles aren't similar. Okie dokie. What do I have next? Let's see. Next we have okay, so moving on, we have another condition for similarity. We just did side angle side. There's another one that doesn't have any angles at all in it, and that is if all 3 sides of one triangle are proportional to all 3 sides of another, then the 2 triangles are similar. So if all the sides change by the same amount, by the same scale factor, then they're going to have to be similar. This is called side, side, side similarity. So using the definition above, we're going to look at these triangles. Now, when you compare triangles, you don't always want to do left versus right, which is what I indicated kind of in the beginning as an easier way to think about it. When you want to compare things, you really want to compare small, medium, and large. So when I'm dealing with these 2 triangles, the smallest side of the first triangle is 8, the medium side is 10, and the large side is 11. So small, medium, large, 8, 10, 11. Then I want to do the same thing here. Small, 1.6, medium 2, large 2.2. I want to know if these guys are all equal. So in the calculator here, you can do that. You can do it with fractions, or you don't have to worry about the fractions. If I shrink this a little bit, I can just do 8 divided by 1.6 is 5, 10 divided by 2 is 5, and 11 divided by 2.2 is 5. So these all equal 5. So all the sides are proportional. Therefore, the triangles are similar by side, side, side similarity. And the similarity statement is the one where I say triangle blah, blah, blah is similar to triangle blah, blah, blah. So my first triangle, let's go with cat. And when I write cat, I'm going from the medium side through the big side. So over here, I want to go medium to big. So P, G, I. That seems about right. All right, now let's look at the next one together. Here's R, E, I, and J, C, O. Are these guys similar? I'm going to do small, medium, large again. So if you don't think you need to listen to me as I do this, try and do it on your own. So small, medium, large. That's going to be 2.82, 5.4, and 7. And 1.41, 2.7, and 3.5. And if I do the division here, that's going to be 2. So is that, and so is that. So the sides are proportional. Therefore, triangle REI, which goes from small to medium, is similar to OJC. Then, this is actually the same exact diagram, only shaded here. On C, it says if you can establish that they're similar, which we did, indicate the scale factor. Well, the scale factor is the one that's going to take this triangle onto that triangle. And we just showed right here that the big one is twice as big as the small one. So the scale factor taking me from big back to small would be a half. Almost done. Hang with me, almost done here. So, we have now, in the last 2 lessons, found 3 conditions for proving things similar. The first condition I think is the easiest. That's angle-angle similarity. The other 2 are side-angle-side similarity and side-side-side similarity. And basically, if you can find 2 angles that are the same, you know they're similar. If you can find 2 sides that are proportional with a congruent included angle, they're similar. Or if you have no angles at all, you go with side, 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 and make sure all 3 sides give you a consistent proportion. So, I would like you to probably stop here, and then tomorrow when you come to class, your assignment is going to be to do example 1 and example 2 on this page, and then move on to do the problem set that follows. So, that is what we have. If you have any questions, you can refer to the notes answer key that will be posted either on my calendar and or on our geometry page. And this is Mod 2 Topic C. So feel free to look for anything you need, and I will be speaking with you soon. All right, so we need a joke. A Christmas joke today is, what do elves study at school? The alphabet. Have a good day.